All right, welcome to physics lesson 7.04 over energy. And let's be more specific. Let's say, whoops, my pen's starting to go dry. We're talking about mechanical energy. So in our first video over energy, we had all of the little bubbles. We had the nuclear and the electromagnetic and the electrical. And we said in this course, in this time, we're dealing with mechanical energy. And we said we could split that out into two different categories. We could have potential and we could have kinetic. And with the potential, we're going to work with two different kinds of potential. We've got gravitational potential energy, gravitational, and we have spring potential. Gravitational potential energy and spring potential energy. And so what I want to do, the goal of this video is to introduce all three of these, and we have a sample problem to go with them. So starting off is sample problem 5. So the problems are labeled in this packet. We've got a 3,900 kilogram truck is moving at 6, that should say meters per second. What is the truck's kinetic energy? So we said the definition of energy is the ability to do work, and that's going to be up here with the potentials. This is the ability, or actually having the act of doing work. So kinetic is the action. This is where we get to see work coming into play, and we see a change in movement. So this is going to be related to movement. And in order to measure potential energy, we have to have a reference point. So we're talking about energy from between 2 points. We have to have 2 points, a reference point and then a point we're measuring. But for both of these, what we see is we're looking at a change in energy. So when we look at kinetic energy, we're usually considering, when we use it in any kind of an application, the difference in kinetic energy between 2 points. Or if we're looking at gravitational or spring, we're looking at, like, for example, with gravitational, we look at the ground versus the height. But let's start off here with kinetic energy. The formula for kinetic energy, usually abbreviated as KE, is 1/2 mass times velocity squared. A couple of things to notice. We have not just straight velocity, but it's velocity squared. So we can see velocity is going to have a pretty big impact on this expression. And mass does as well, but not to the same extent that velocity does. So if we're looking at units for this, we've got mass is kilogram, and velocity is meters per second, and we're going to square that. So that gives us kilogram meters squared over seconds squared, and we said that's equal to a joule. And as we mentioned last time, gosh, this really looks blurry. I don't know what my deal is. Let's see if I can focus this up. I'm going to try to take my a little better. When we talk about work, we usually use the Newton meter, and we talk about energy, we usually use the joule, even though they're the exact same thing. So if I wanted to find this initial kinetic energy, I'm going to take 1/2 times 3,900 times 6 squared. And that's going to give me 70,200 joules. When I look at this, if I double the speed, you know, if this was a 1-to-1, you would expect that to double. But what we see instead is that this goes up to 280,800 joules. So it is an exponential relationship because of the velocity. We usually use kilojoules just because a joule really isn't that much energy. And so it's not unusual to see in problems kilojoules. All right, for the next problem, we're going to be talking about gravitational potential energy. So here we have gravitational potential energy. Potential energy is usually abbreviated as a giant U, and then we'll use U sub G to indicate that this is gravitational. It is equal to mass times the acceleration due to gravity. Now, this is the same thing as A sub G. Little g and A sub G are the same thing. Again, I've always emphasized A sub G because I don't want you to make the mistake of thinking this is a force times height. When I look at my units here, I have kilograms times acceleration due to gravity is meters per second squared. Height is going to be in meters. So you can see I'm still at that kilogram, meters squared over second squared. So my units are consistent. My units are going to be joules. So what we want to talk about here is the fact height. So I've got this cliff diver. Wow, this pen is definitely done. Trash you go. All right, I'll use brown. So I've got this cliff diver, and it says his height is 46 meters. Well, what we just did was the implication here is that the ground is 0. So we automatically put in a reference point that we're looking at 46 meters above the ground, even though the problem says, it just says he jumps from a height, he drops to the water from a height of 46 meters. Actually, this would be the surface of the water. So this reference point is arbitrary. Arbitrary means you get to pick whatever you want to be 0. And we've seen this before when we did kinematics. We got to pick our 0 point. So when we look at this gravitational potential energy, though, what I have to say is I'm comparing it between here and here. And this comes into play where we can't just say, I can't look at a spot in any given system and say, this is the energy for this object at that spot. It's a comparison. It's delta. It's a change. And that's what we have here. So the problem says his gravitational energy decreases by 25,000 joules. So when he jumps from here to here, U sub G goes down by 25,000 joules. What tells us is if I take UG is 25,000, my height is 46 meters, little g is 9.81 meters per second squared. So if I want to solve for mass, I can do that. It's going to be 25,000 equals mass times 9.81 times 46. And his mass, when I solve, is going to be 55.4 kilograms. All right, finally, let's look at spring potential energy. Slide my sheet here. This is in examples of where we have a spring we're directly using, where we're going to launch something off of a spring, or maybe like a mousetrap, a circular spring. We could use it in the example of a mousetrap, or anything with a loaded hinge. What we see is the formula for, we're going to use purple. So spring potential energy. Is going to be U sub S or U sub E, because it's also called elastic potential energy. Actually, that's more common than spring potential energy, elastic potential energy. And this is the more common term that you're going to have is UE. UE is equal to 1/2 kx squared. K is what is known as the spring constant. And the higher the value here, higher the value, the stiffer the spring. Stiffer the spring. So a spring that doesn't bend very easily might have a spring constant of 2 or 3,000. Now we're looking at a spring constant that has 120, and the unit is a Newton over a meter. So it's a Newton meter, not Newton times meter, a Newton divided by a meter. X is the distance the spring is compressed. Distance the spring is compressed. So and that's in meters. Remember, we have to keep everything consistent. When I work this Newton meter and I do this meter squared, that's going to still give me at the end. So if I look at my unit here, this is going to be a Newton meter and this is squared. So it's going to be a Newton meter times a meter squared. It's going to cancel and you're going to end up with a Newton meter, which is equal to a joule. So same unit. What we see is the further I compress the spring, the greater my elastic potential energy is. And that makes sense. If you think about putting a spring at about halfway and letting it recoil versus pushing it in the whole way and letting it recoil, you're going to have a much greater response if you compress the spring further. So we have a spring constant with 120 Newton meters is compressed a distance of 2.3 centimeters. How much potential energy is stored in the spring? So my elastic potential energy is 1/2. I've got 120 here. And this then is going to be, I have to convert that to meters. So that is going to be 0.023 meters, and that's going to be squared. I have to punch this one in my calculator. 23 squared times 120. And we get a elastic potential energy of 0.031 joules. Let's double check that. Yeah. Okay, so that is your introduction to our 3 main types of mechanical energy that we're going to be using, kinetic, and then 2 types of potential. And we're going to start to look at how we use conservation of energy and something called the work energy theorem to really kind of get into the meat and potatoes of this chapter. All right, that's all for now.